OpenID Connect PKCE workflow. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics, with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving into one of the most important security enhancements in modern authentication: the OpenID Connect PKCE workflow. PKCE stands for Proof Key for Code Exchange, and it is pronounced PKCE. This mechanism was originally designed to protect mobile and native applications, but it has become so effective that it is now recommended for all types of OAuth 2.0 and OpenID Connect implementations, including web applications. The fundamental problem that PKCE solves is the authorization code interception attack. In the traditional OAuth 2.0 authorization code flow, there was a vulnerability window where an attacker could intercept the authorization code as it is being returned to the application. This was particularly problematic for mobile applications and single-page applications that could not securely store client secrets. PKCE eliminates this vulnerability by creating a cryptographic link between the authorization request and the token request, making it impossible for an attacker to use an intercepted code. In this presentation, we will explore the complete PKCE workflow step by step. We will examine how the code verifier and code challenge are generated, how they are used throughout the authentication process, and why this mechanism provides such strong security guarantees. We will also look at the cryptographic foundations that make PKCE work, including SHA-256 hashing and base64 URL encoding. Understanding PKCE is essential for anyone implementing modern authentication systems, whether you are building mobile apps, single-page applications, or traditional web applications. The PKCE security problem. Before we dive into how PKCE works, it is crucial to understand the exact security problem it was designed to solve. The traditional OAuth 2.0 authorization code flow had a significant vulnerability which was particularly apparent in mobile and native applications. Let me walk you through this attack scenario in detail. In a typical OAuth 2.0 flow without PKCE, when a user wants to authenticate, the client application redirects them to the authorization server. After the user successfully authenticates and grants permission, the authorization server generates an authorization code and redirects the user back to the client application with this code included in the URL. Here is where the problem arises. This redirect happens through the user's browser or system browser on mobile devices. An attacker who has managed to install malicious software on the user's device could register itself as a handler for the same redirect URI scheme. When the authorization server tries to redirect back to the legitimate application with the authorization code, the operating system might deliver that redirect to the malicious application instead. The attacker now has the authorization code. In the traditional flow, this code alone could be exchanged for access tokens if the client is a public client that cannot securely store a client secret. This attack is called authorization code interception, and it is particularly dangerous because it completely bypasses user authentication. The user thinks they have successfully logged into the legitimate application, but the attacker has actually obtained credentials that allow them to impersonate the user. This is not just a theoretical vulnerability. It is a real attack that has been demonstrated in practice, particularly against mobile applications. PKCE was specifically designed to prevent this attack by creating a cryptographic binding between the initial authorization request and the subsequent token request. Even if an attacker intercepts the authorization code, they cannot use it to obtain tokens because they don't possess the secret value that was used to generate the code challenge in the initial request. This makes PKCE a critical security enhancement for any OAuth 2.0 or OpenID Connect implementation. PKCE cryptographic components. PKCE's security relies on two fundamental cryptographic components: the code verifier and the code challenge. Understanding how these components are generated and used is essential to understanding how PKCE provides its security guarantees. Let's break down each component in detail. The code verifier is a cryptographically random string that the client application generates at the very beginning of the authentication flow. According to the PKCE specification, this must be a random string between 43 and 128 characters long, using only unreserved characters from the URI specification. These characters include uppercase and lowercase letters, digits, hyphen, period, underscore, and tilde. The code verifier must have sufficient entropy to be unguessable. Typically, implementations generate this by creating 32 random bytes and then base 64 URL encoding them, which produces a 43-character string. The code challenge is derived from the code verifier through a cryptographic transformation. The PKCE specification defines two methods for creating this challenge: plain and S256. The plain method simply uses the code verifier itself as the challenge, but this provides no actual security benefit and should never be used. The S256 method, which is the only method that should be used in practice, creates the challenge by first computing the SHA-256 hash of the code verifier, and then base 64 URL encoding the resulting hash value. The reason we use SHA-256 hashing is that it is a one-way function. Given the code challenge, it is computationally infeasible to determine what the original code verifier was. This is crucial for the security model. The client sends the code challenge to the authorization server in the initial request, but keeps the code verifier secret. The authorization server stores the code challenge associated with the authorization code it issues. Later, when the client exchanges the authorization code for tokens, it must provide the original code verifier. The authorization server can then hash this verifier using SHA-256 and verify that it matches the challenge it stored earlier. The base 64 URL encoding is used because both the verifier and the challenge need to be transmitted in URLs and HTTP headers, which have restrictions on which characters can be used. Base 64 URL encoding is a variant of standard base 64 that replaces characters that have special meaning in URLs plus and slash with URL safe alternatives hyphen and underscore, and omits the padding characters. This ensures that the values can be safely transmitted through all the various systems involved in the authentication flow. The beauty of this design is that even if an attacker intercepts the authorization code and sees the code challenge that was sent in the initial request, they cannot determine the code verifier needed to complete the token exchange. The one-way nature of the SHA-256 hash function makes it computationally infeasible to reverse the challenge back to the verifier, even though both values may be visible in network traffic or browser history. Complete PKCE flow overview. Now that we understand the cryptographic components, let's walk through the complete PKCE flow from start to finish. This flow involves four main actors: the user, the client application, also called the relying party, the authorization server, and the resource server. Each of these plays a specific role in the authentication and authorization process. The flow begins when the user initiates a login action in the client application. This could be clicking a sign-in button or trying to access a protected resource. At this moment, the client application must perform its first PKCE-specific action. It generates a cryptographically random code verifier. As we discussed, this is typically 32 random bytes that get base 64 URL encoded into a 43-character string. The client must store this code verifier securely because it will need it later. Next, the client computes the code challenge by taking the SHA-256 hash of the code verifier and base 64 URL encoding the result. The client then constructs the authorization request URL. This is a redirect to the authorization server that includes several important parameters: the client ID that identifies the application, the redirect URI where the response should be sent, the response type which is code for the authorization code flow, the scope which defines what permissions are being requested, and critically for PKCE, the code challenge and the code challenge method which should be S256. The client redirects the user's browser to this authorization URL. The user is now interacting directly with the authorization server. The authorization server will present a login interface and ask the user to authenticate. This might involve entering a username and password, or using some other authentication method like biometrics or a hardware token. After successful authentication, the authorization server will also ask the user to consent to the permissions that the client application is requesting. Once the user has authenticated and consented, the authorization server generates an authorization code. Here's where PKCE comes into play on the server side. The authorization server must store the code challenge value that was provided in the authorization request, associating it with this specific authorization code. This binding is crucial for the security of the flow. The authorization server then redirects the user's browser back to the client application's redirect URI, including the authorization code as a parameter in the URL. The client application receives this redirect at its specified redirect URI. It extracts the authorization code from the URL parameters. Now comes the critical moment where PKCE proves its worth. The client makes a direct back-channel request to the authorization server's token endpoint. This request includes the authorization code it just received, but it also includes the original code verifier that it generated at the very beginning of the flow. The client is essentially proving that it is the same application that initiated the authorization request. The authorization server receives the token request with the code verifier. It retrieves the code challenge that it stored when it issued the authorization code. It then performs the same transformation on the received code verifier. It computes the SHA-256 hash and base 64 URL encodes it. If this computed value matches the stored code challenge, the authorization server knows that the request is coming from the legitimate client application that initiated the flow. Only the application that generated the original code verifier could provide this matching value. If verification succeeds, the authorization server issues the ID token, access token, and optionally a refresh token. This is how PKCE defeats the authorization code interception attack. Even if an attacker intercepts the authorization code, they don't have the code verifier. They might have seen the code challenge that was sent in the authorization request, but because of the one-way nature of SHA-256, they cannot determine the verifier from the challenge. Without the correct code verifier, they cannot complete the token exchange. The authorization server will reject any token request that doesn't include the matching code verifier, effectively rendering the intercepted authorization code useless to the attacker. Initial authorization request. Let's examine the initial authorization request in detail, as this is where the PKCE flow begins and where the cryptographic binding is established. This request is the foundation of the entire security mechanism, and understanding its components is crucial. The authorization request is constructed as an HTTP GET request to the authorization server's authorization endpoint. This endpoint URL is typically something like https://auth.example.com/authorize. The request includes several parameters that are added to the URL as query parameters. Let me walk through each one and explain its purpose. The response type parameter is set to code. This tells the authorization server that we are using the authorization code flow, as opposed to other OAuth 2.0 flows like the implicit flow. The authorization code flow is the most secure option and is the recommended flow for almost all scenarios today. By specifying code, we are telling the server that we want it to return an authorization code, which we will later exchange for tokens. The client ID parameter identifies which application is making the request. Every client application that wants to use the authorization server must be registered in advance, and during registration, it receives a unique client ID. This identifier is not secret, it is essentially public information. The authorization server uses the client ID to look up the application's configuration, including its allowed redirect URLs and the permissions it is allowed to request. The redirect URI parameter specifies where the authorization server should send the response. For security reasons, this URI must exactly match one of the redirect URIs that was registered for this client ID. The authorization server will reject the request if the redirect URI does not match a registered value. This prevents an attacker from redirecting the authorization response to their own controlled endpoint. For mobile apps, this might be a custom URI scheme like myapp://callback. For web apps, it is typically an HTTPS URL. The scope parameter defines what permissions the application is requesting. In OpenID Connect, the scope must include OpenID to indicate that this is an OpenID Connect request rather than plain OAuth 2.0. Additional scopes might include profile to request access to the user's profile information, email to request the email address, or custom scopes specific to your API like read documents or write data. The authorization server will show these requested scopes to the user during the consent screen. The state parameter is a security measure to prevent cross-site request forgery attacks. The client generates a random value, includes it in the authorization request, and stores it locally. When the authorization server redirects back with the response, it includes this same state value. The client must verify that the state in the response matches the state it generated. This ensures that the response is legitimate and corresponds to a request that the client actually initiated. Now we come to the PKCE specific parameters. The code_challenge parameter contains the base 64 URL encoded SHA-256 hash of the code verifier. This is the value that the authorization server will store and later use to verify the token exchange request. Remember, the actual code verifier is never sent at this stage, only the challenge is sent. The one-way nature of the hash function ensures that even if this request is intercepted, the attacker cannot determine the verifier from the challenge. The code challenge method parameter specifies which method was used to generate the challenge from the verifier. This should always be S256 in modern implementations, indicating that SHA-256 hashing was used. The specification also defines a plain method where the challenge equals the verifier, but this provides no security benefit and should never be used. If an authorization server receives a request with the plain method, it should reject it or downgrade gracefully while warning about the security implications. When the client constructs this URL with all these parameters, and redirects the user's browser to it, the user is taken to the authorization server's login page. The authorization server receives all these parameters, validates them, and begins the authentication process. Critically, it stores the code challenge value associated with the session, so it can verify it later when the client exchanges the authorization code for tokens. User authentication and consent. After the client redirects the user to the authorization server, the user enters the authentication and consent phase. This is where the user directly interacts with the authorization server to prove their identity and grant permissions to the client application. Let us examine what happens during this critical phase. When the user's browser lands on the authorization server, the first thing that happens is authentication. The authorization server needs to verify that the user is who they claim to be. The specific authentication method depends on the authorization server's configuration and the organization's security policies. The most common method is username and password, where the user enters their credentials into a form presented by the authorization server. However, modern authorization servers support a variety of authentication methods. Multi-factor authentication, MFA, is becoming increasingly common, where the user must provide a second factor beyond their password. This might be a time-based one-time password, TOTP, from an authenticator app, a code sent via SMS, a push notification to a mobile device, or a biometric factor like a fingerprint or face recognition. Some organizations use hardware security keys that implement standards like FIDO2 or WebAuthn for phishing-resistant authentication. The authorization server might also have session management capabilities. If the user has recently authenticated to the authorization server for another application, they might already have an active session. In this case, the authorization server can recognize the user from their session cookie and skip the authentication step entirely, or it might require re-authentication depending on security policies and the sensitivity of the requested resources. After successful authentication, the authorization server presents a consent screen. This screen shows the user which application is requesting access and what permission scopes it's requesting. The consent screen is a critical security and privacy feature. It gives the user visibility into what the application wants to access and allows them to make an informed decision about whether to grant that access. The consent screen typically displays the application's name, its logo, and a description of what it does. Below this, it lists the specific permissions requested in user-friendly language. For example, instead of showing the technical scope read :contacts, it might say read your contact list. The user can then choose to approve or deny the request. Some authorization servers also allow users to modify the requested permissions, granting only a subset of what the application requested. It is important to understand that the consent step is not just a formality. It is a crucial part of the OAuth 2.0 security model. Even though the application developer might trust their own application, the user needs to explicitly consent to the access. This prevents scenarios where an application might request excessive permissions without the user's knowledge. The consent requirement also means that even if an attacker tricks a user into initiating an OAuth flow, the user will see the consent screen and might recognize that something is wrong. Once the user clicks the Approve button on the consent screen, the authorization server processes the decision. It records the user's consent decision, which might be stored for future requests from the same application, avoiding the need to show the consent screen every time. The server then generates an authorization code, which is a short-lived, one-time use token. This code is essentially a reference that the client will later exchange for actual access tokens. Here's a crucial point regarding PKCE. When the authorization server generates this authorization code, it must associate it with the code challenge that was provided in the initial authorization request. This association is typically stored in a server-side database or cache. The code has a short lifetime, usually between 1 to 10 minutes. The server also associates the code with other context about the request, including the client ID, the redirect URI, the requested scopes, and the user who granted consent. All of this information will be validated when the client later attempts to exchange the code for tokens. Authorization response and code exchange. After the user authenticates and consents, the authorization server generates an authorization code and needs to return it to the client application. This is done through a redirect back to the client's registered redirect URI. Let's examine this response and the subsequent token exchange in detail. The authorization server constructs a redirect URL, using the redirect URI that was provided in the authorization request. It adds the authorization code as a query parameter. The URL will look something like this: https://myapp.example.com/callback code auth code here and sign state state value. Notice that the state value, which the client included in the original request, is also returned. This allows the client to verify that this response corresponds to a request it actually initiated. The authorization server sends an HTTP 302 redirect response to the user's browser, pointing to this constructed URL. The browser automatically follows the redirect, making a request to the client application's redirect URI with the authorization code included. This means the authorization code briefly appears in the browser's address bar and in the browser history. This is not a security problem because the code alone is useless without the code verifier, which is the whole point of PKCE. When the client application receives the request at its redirect URI, it must perform several validation steps. First, it extracts and validates the state parameter. It compares this value to the state it generated and stored before initiating the authorization request. If the state values do not match, the client must reject the response because it might be a cross-site request forgery attack. If the state matches, the client knows this is a legitimate response to a request it initiated. Next, the client extracts the authorization code from the query parameters. It also retrieves the code verifier that it generated at the very beginning of the flow and has been storing securely. Now comes the crucial step. The client makes a direct server-to-server request to the authorization server's token endpoint to exchange the authorization code for tokens. This token request is an HTTP POST request to the token endpoint, typically at a URL like https://auth.example.com/token. The request includes several parameters in the post body, using the application/xwww form URL encoded content type. Let me explain each parameter in this critical request. The grant type parameter is set to authorization code. This tells the authorization server that we are exchanging an authorization code for tokens, as opposed to other OAuth 2.0 grant types like refresh token or client credentials. The code parameter contains the authorization code that was just received. The client ID parameter identifies which client is making the request, just as in the authorization request. The redirect URI parameter must be included and must exactly match the redirect URI that was used in the authorization request. The authorization server validates this to ensure that the token request is coming from the same client that received the authorization code. This prevents an attacker who might have intercepted the code from using it with a different redirect URI. Finally, and most critically for PKCE, the code verifier parameter contains the original random string that was generated at the beginning of the flow. This is the secret value that only the legitimate client possesses. Remember, what was sent in the authorization request was the code challenge, which is the SHA-256 hash of this verifier. Now the client is proving its identity by providing the original verifier. When the authorization server receives this token request, it performs the PKCE verification. It retrieves the code challenge that it stored when it issued the authorization code. It takes the code verifier from the request, computes its SHA-256 hash, and base 64 URL encodes the result. It then compares this computed value to the stored code challenge. If they match, the verification succeeds, proving that the request is coming from the legitimate client. If they do not match, the server immediately rejects the request. Token response and validation. When the authorization server successfully validates the code verifier and all other parameters in the token request, it issues the tokens and returns them to the client. This token response contains several important components that the client will use for authentication and authorization. Let's examine each component in detail. The response is returned as a JSON object in the HTTP response body. The most important component is the ID token. This is a JSON web token, JWT, that contains claims about the authentication event and the user's identity. The ID token is specifically part of OpenID Connect and is what distinguishes OpenID Connect from plain OAuth 2.0. It allows the client to verify who the user is and when they authenticated. The ID token has three parts separated by dots: the header, the payload, and the signature. The header contains metadata about the token, including which algorithm was used to sign it. The payload contains the claims, which are statements about the user and the authentication. These claims include standard ones like sub for the subject identifier, a unique identifier for the user, ISS for the issuer, the authorization server that issued the token, AUD for the audience, the client ID that the token is intended for, express for the expiration time, and IAT for the time the token was issued. The signature is computed over the header and payload using a private key held by the authorization server. The client can verify this signature using the authorization server's public key, which is typically published at a well-known endpoint. This verification ensures that the token was actually issued by the trusted authorization server and hasn't been tampered with. The signature is what makes JWTs secure and allows them to be transmitted through untrusted channels. In addition to the ID token, the response includes an access token. While the ID token is about authentication and identifies the user, the access token is about authorization and grants access to resources. The access token is what the client will include in requests to resource servers, APIs, to prove that it has permission to access protected resources on behalf of the user. Access tokens can be JWTs, but they can also be opaque strings that the resource server validates by calling back to the authorization server. The token response also includes a token underscore type parameter, which is almost always bearer. This indicates that the access token should be included in API requests using the HTTP authorization header with the bearer authentication scheme. The response includes an expires underscore in parameter, which tells the client how many seconds until the access token expires. Typical lifetimes range from 1 hour to 24 hours, depending on security requirements. If the client requested the offline access scope and the authorization server supports it, the response will also include a refresh token. This is a long-lived token that the client can use to obtain new access tokens after the current access token expires, without requiring the user to authenticate again. Refresh tokens are particularly important for applications that need long-term access to resources. However, they must be stored very securely because anyone who possesses a refresh token can obtain access tokens. The response might also include additional fields depending on the authorization server's implementation. There might be a scope parameter that indicates which scopes were actually granted, which might be different from what was requested if the user modified the permissions during consent. Some implementations include additional information in custom parameters. When the client receives this token response, it must perform several validation steps on the ID token before trusting it. It must verify the signature using the authorization server's public key. It must verify that the issuer claim matches the expected authorization server. It must verify that the audience claim matches its own client ID. It must verify that the token hasn't expired by checking the expiration claim against the current time. It must also verify the nonce claim if it included a nonce in the authorization request, which is an additional security measure similar to the state parameter. After all these validations pass, the client can extract the user's identifier from the subject claim and establish an authenticated session for the user. It can store the access token securely and use it to make API calls on behalf of the user. If a refresh token was included, the client should store it in the most secure storage available, such as encrypted storage or a secure keychain on mobile devices. PKCE security benefits. Now that we've walked through the complete PKCE flow, let's examine the specific security benefits it provides and why it's become a mandatory recommendation for OAuth 2.0 and OpenID Connect implementations. Understanding these benefits will help you appreciate why PKCE is so important in modern authentication systems. The primary security benefit of PKCE is protection against authorization code interception attacks. In the traditional OAuth 2.0 flow without PKCE, if an attacker could intercept the authorization code as it is being returned to the client, they could potentially exchange that code for tokens. This was especially problematic for public clients, like mobile apps, that cannot securely store client secrets. With PKCE, even if an attacker intercepts the authorization code, they cannot use it because they do not possess the code verifier. The code challenge that they might have seen in the initial request is cryptographically transformed from the verifier in a way that cannot be reversed. PKCE eliminates the need for client secrets in public clients. In traditional OAuth 2.0, confidential clients like traditional web applications running on secure servers could protect themselves by using a client secret. During the token exchange, they would send both the authorization code and the client secret, proving their identity. However, public clients like mobile apps, single-page applications, and native desktop applications cannot securely store secrets because their code can be inspected or decompiled. PKCE provides an alternative authentication mechanism that doesn't rely on a pre-shared secret, making it perfect for these types of clients. Another important benefit is protection in compromised environments. If a user's device has been compromised by malware, that malware might attempt to register itself as a handler for the client's redirect URI scheme. When the authorization server tries to redirect back with the authorization code, the malware could intercept it. However, with PKCE, the malware still cannot complete the token exchange because it doesn't have access to the code verifier that was generated by the legitimate application. The code verifier is generated in the legitimate app's process space and never leaves it until the token exchange, making it much harder for malware to steal. PKCE also provides defense in depth. Even in scenarios where client secrets could theoretically be used, PKCE adds an additional layer of security. This follows the security principle that multiple independent security mechanisms are better than relying on a single mechanism. If there is a vulnerability in how client secrets are handled, PKCE still provides protection. This is why current best practices recommend using PKCE even for confidential clients that also use client secrets. The security of PKCE relies on the cryptographic properties of SHA-256. This hash function is one-way, meaning it is computationally infeasible to determine the input, code verifier, from the output, code challenge. It is also collision-resistant, meaning it is computationally infeasible to find two different inputs that produce the same output. These properties ensure that an attacker cannot forge a valid code verifier, even if they have seen the code challenge. The 256-bit output of SHA-256 provides more than sufficient security for this purpose. PKCE is particularly important for mobile and native applications because of their unique security characteristics. These applications run in environments where the user has full control over the device and can inspect or modify the application's behavior. They also use custom URI schemes for redirects, which can be registered by multiple applications on the same device. PKCE was originally designed specifically to address these mobile security concerns, but its effectiveness has led to its adoption across all types of OAuth 2.0 clients. Another benefit is that PKCE works transparently with the standard OAuth 2.0 and OpenID Connect protocols. Authorization servers that support PKCE can continue to work with older clients that do not use PKCE, while providing enhanced security for clients that do implement it. This backward compatibility has been crucial for the widespread adoption of PKCE. Clients can implement PKCE without requiring changes to resource servers or other parts of the system. From a threat modeling perspective, PKCE significantly reduces the attack surface. Without PKCE, an attacker only needs to intercept the authorization code to compromise the authentication. With PKCE, an attacker would need to compromise the client application's process space to steal the code verifier, which is a much higher bar. This moves the security boundary from the network layer, where interception is relatively easy, to the process isolation layer, where attacks are much more difficult. Implementation best practices. Implementing PKCE correctly is crucial for achieving its security benefits. There are several best practices and important considerations that developers need to be aware of when implementing PKCE in their applications. Let's walk through these recommendations in detail. The first and most important best practice is to always use the S256 code challenge method. Never use the plain method, even if the authorization server supports it. The plain method offers no security benefit and defeats the entire purpose of PKCE when the code challenge method is plain. The code challenge is identical to the code verifier. This means an attacker who intercepts the authorization request can simply use the code challenge value as the code verifier in the token exchange. Always specify code challenge method equals S256 in your authorization requests. The code verifier must be generated with sufficient entropy. The specification requires at least 43 characters and allows up to 128 characters. A common and secure approach is to generate 32 random bytes using a cryptographically secure random number generator, and then base 64 URL encode them. This produces exactly 43 characters and provides 256 bits of entropy, which is more than sufficient for security. Never use predictable values like timestamps or sequential numbers for the code verifier. The code verifier must be stored securely on the client side, between the authorization request and the token exchange. For mobile applications, use the platform's secure storage mechanisms, such as the iOS keychain or Android key store. For single-page applications, store the code verifier in memory only. Never store it in local storage or session storage, where it could be accessed by malicious scripts. For traditional web applications, store it in server-side session storage, with appropriate security controls. Always validate the state parameter in the authorization response. Generate a random state value before initiating the authorization request, store it securely, and verify that the state in the response matches exactly. This protects against cross-site request forgery attacks. The state should be generated with the same level of randomness as the code verifier, using a cryptographically secure random number generator. When implementing the token exchange, always validate that the authorization code is used only once. Authorization codes must be single-use tokens. If an authorization server receives a token request with a code that has already been used, it should reject the request and potentially revoke any tokens that were previously issued using that code. This prevents replay attacks where an attacker might try to reuse an intercepted authorization code. Set appropriate expiration times for authorization codes. They should be short-lived, typically between 1 and 10 minutes. This limits the window during which an intercepted code could potentially be exploited. The authorization code should also be bound to the client that requested it, and the authorization server should verify the client ID in the token exchange matches the client ID from the authorization request. For the hash computation, ensure you are using a proper SHA-256 implementation from a trusted cryptographic library. Do not try to implement SHA-256 yourself. Use standard libraries like the Web Crypto API in browsers, Common Crypto on iOS, or the Java Security API on Android. After computing the SHA-256 hash, make sure to base 64 URL encode it correctly. Base 64 URL encoding is slightly different from standard base 64 encoding. It uses hyphen instead of plus, underscore instead of slash, and omits the padding equals signs. When constructing authorization requests, always use HTTPS for redirect URLs in web applications. For mobile applications, use custom URI schemes, but be aware of the security considerations. On iOS, use universal links when possible as they provide better security against URI scheme hijacking. On Android, use app links to bind your application to a specific domain. These mechanisms provide better security than custom URI schemes alone. Consider implementing additional security measures beyond PKCE. Use the nonce parameter in OpenID Connect requests to prevent token replay attacks. Implement proper token validation, including signature verification, issuer validation, audience validation, and expiration checking. Test your PKCE implementation thoroughly. Verify that the authorization server properly stores and validates the code challenge. Test your PKCE implementation thoroughly. Verify that the authorization server properly stores and validates the code challenge. Test that authorization codes cannot be used more than once. Test that token requests with incorrect code verifiers are rejected. Test the complete flow from authorization request through token exchange to ensure all the pieces work together correctly. Consider using automated testing tools and security scanning tools to verify your implementation. Mobile Application PKCE Implementation. Mobile applications represent one of the most critical use cases for PKCE because they face unique security challenges that make traditional OAuth 2.0 flows vulnerable. Let's explore in detail how PKCE is implemented in mobile applications, the specific security considerations, and the platform-specific mechanisms that enhance security. Mobile applications are considered public clients in OAuth 2.0 terminology, which means they cannot securely store client secrets. The application binary can be decompiled or inspected, making any secrets embedded in the code discoverable. This is fundamentally different from server-side web applications that can store secrets in secure server environments. Before PKCE, this limitation made mobile applications vulnerable to authorization code interception attacks. On iOS, the recommended approach for OAuth 2.0 and OpenID Connect is to use a web authentication session, which is Apple's built-in API for web-based authentication. This API presents a secure browser session that is isolated from the application. The user can see the URL and verify they are actually communicating with the real authorization server. AS Web Authentication Session also integrates with the system's single sign-on capabilities, so if the user has already authenticated in Safari or another app using the same authorization server, they might not need to enter credentials again. For the redirect URI on iOS, you have two primary options. The first is custom URI schemes, like my app://callback. These are easy to implement but have a security limitation. Any application can register the same scheme, potentially intercepting the callback. The second and more secure option is universal links, which use HTTPS URLs that are cryptographically bound to your application through an association file hosted on your domain. Only your application can handle these URLs, preventing hijacking attacks. When implementing PKCE on iOS, you should prefer universal links whenever possible. On Android, the situation is similar, but with platform-specific details. The recommended approach is to use Chrome Custom Tabs, which provides a secure browser environment within your application's context. Chrome Custom Tabs offer better security than WebView because they run in a separate process and can't be manipulated by the application code. They also support autofill and other browser features that improve user experience. For Android redirect URIs, you can use either custom schemes or app links. App links are Android's equivalent to iOS universal links. They use HTTPS URLs and require you to host a digital asset links file on your domain. This file cryptographically proves that your application is associated with the domain, preventing other apps from intercepting the redirects. The Android system verifies this association and ensures only your application handles the URLs. When implementing code verifier generation on mobile platforms, you must use the platform's cryptographically secure random number generator. On iOS, this is sec random copy bytes from the security framework. On Android, use secure random from java.security. Never use predictable sources of randomness, like timestamps or device identifiers. The code verifier should be generated fresh for each authentication flow, and should never be reused across different authentication attempts. Storage of the code verifier during the authentication flow is crucial. The verifier needs to be kept secure from the moment it is generated until it is used in the token exchange. On iOS, the most secure option is to store it in the keychain with appropriate protection attributes. The keychain can be configured to require device unlock for access and can use the secure enclave on devices that support it. On Android, use the key store system, which can leverage hardware-backed security on supported devices. For very short-lived storage during the authentication flow, keeping the verifier in memory only is also acceptable, but you need to handle application backgrounding and termination correctly. The complete mobile PKCE flow involves several coordinated steps. First, your application generates the code verifier and computes the code challenge. It stores the verifier securely and constructs the authorization URL with all required parameters, including the code challenge. The application then initiates a web authentication session on iOS or Chrome custom tabs on Android, passing the authorization URL. The user is taken through the authentication and consent flow in this secure browser context. After the user approves, the authorization server redirects back to your application's registered URI with the authorization code. Your application receives this through the system's URL handling mechanism, validates the state parameter, retrieves the stored code verifier, and makes the token exchange request including the verifier. The authorization server validates the verifier matches the challenge and returns the tokens. Single-page application PKCE implementation. Single-page applications, or SPAs, present a different set of security challenges compared to mobile applications. SPAs are JavaScript applications that run entirely in the browser, communicating with backend APIs through HTTP requests. Like mobile apps, SPAs are public clients that cannot securely store secrets. However, they face additional challenges related to the browser security model and cross-origin resource sharing. The traditional approach for SPAs was to use the OAuth 2.0 implicit flow, where tokens were returned directly in the URL fragment after authentication. However, this flow has significant security vulnerabilities. Tokens in URL fragments can leak through browser history, referrer headers, and browser extensions. The implicit flow also does not support refresh tokens for security reasons, forcing users to re-authenticate frequently. Modern best practices strongly recommend against using the implicit flow for SPAs. PKCE with the authorization code flow is now the recommended approach for SPAs. This provides much better security than the implicit flow while maintaining the benefits of a client-side application. The key difference from mobile implementations is that everything happens in the browser environment, which has its own security model and constraints. For code verifier generation in SPAs, you should use the Web Crypto API, which is available in all modern browsers. Specifically, use crypto.get random values to generate cryptographically secure random bytes. This API uses the browser's built-in random number generator, which is properly seeded from system entropy. After generating random bytes, base64 URL encode them to create the code verifier. For the SHA-256 hash needed for the code challenge, use the crypto.subtle.digest function from the Web Crypto API. Storage of the code verifier in SPAs requires careful consideration. The code verifier needs to be available when the authorization server redirects back to your application after authentication. The safest approach is to store the code verifier in memory only, using a JavaScript variable in your application state. This prevents it from being accessible to other scripts or persisting across browser sessions. Never store the code verifier in local storage or session storage, as these are vulnerable to cross-site scripting, XSS, attacks. Any malicious script that can execute in your application's context can read these storage mechanisms. However, in-memory storage has a limitation. If the user closes the tab or browser during authentication, the code verifier is lost. To handle this, you can use session storage as a fallback, but you must implement proper XSS protections. This means having a strong content security policy, sanitizing all user input, and ensuring your application does not execute untrusted scripts. Some developers use the state parameter to store an encrypted version of the code verifier, but this adds complexity and requires careful implementation to avoid security issues. The redirect URI for SPAs is typically the same origin as the application itself, using an HTTPS URL like https://myapp.example.com/callback. When the authorization server redirects back, your SPA needs to extract the authorization code from the URL parameters. Modern JavaScript frameworks and routing libraries usually handle this automatically, but you need to ensure the code is extracted securely and the state parameter is validated before proceeding. Cross-origin resource sharing, CORS, is an important consideration for SPAs implementing PKCE when your SPA makes the token exchange request to the authorization server's token endpoint. This is a cross-origin request because the authorization server is on a different domain. The authorization server must have CORS properly configured to allow requests from your SPA's origin. The CORS preflight request will check if the authorization server allows the post method and the content type header you are using. If CORS is not properly configured, your token requests will fail in the browser. Token storage after successful authentication is another critical consideration. The access token and ID token need to be stored somewhere accessible to your application for making API requests. In-memory storage is the most secure option, but tokens are lost when the tab is closed or refreshed. Session storage is a common choice, allowing tokens to persist across page refreshes but not across tabs or browser sessions. Local storage should be avoided for tokens due to XSS risks. Some applications use HTTP-only cookies for storing tokens, which provides excellent XSS protection, but this requires the token endpoint to set cookies, which is not standard OAuth 2.0 behavior and requires custom backend implementation. The complete SPA PKCE flow starts with the user clicking a login button in your application. Your JavaScript code generates the code verifier using the Web Crypto API and stores it appropriately. It computes the code challenge, constructs the authorization URL with all parameters, and redirects the entire browser window to this URL. The user authenticates with the authorization server, and after approval, the authorization server redirects back to your SPA's callback URL. Your application's JavaScript code runs, extracts the authorization code and state from the URL, validates the state, retrieves the stored code verifier, makes a fetch request to the token endpoint with the code and verifier, receives the tokens, validates the ID token, and establishes the authenticated session. Throughout this process, your application must maintain proper security practices to protect against XSS and CSRF attacks. PKCE error handling and edge cases. Proper error handling is essential for a robust PKCE implementation. The authentication flow can fail at multiple points for various reasons, and your application needs to handle these failures gracefully while maintaining security. Let us examine the different types of errors that can occur and how to handle them appropriately. The first category of errors occurs during the authorization request phase. The user might deny the authorization request by clicking a deny or cancel button on the consent screen. In this case, the authorization server redirects back to your application with an error parameter set to access denied and an error description explaining that the user denied the request. Your application should detect this error, inform the user that they chose not to grant access, and potentially allow them to try again or return to an unauthenticated state. Invalid parameters in the authorization request will cause errors. If the client ID does not match a registered application, the authorization server typically shows an error page rather than redirecting back, since it does not trust the redirect URI without a valid client. If the redirect URI does not match a registered value for the client, the server will reject the request for security reasons. If the scope includes values that the client is not allowed to request, the server might either reject the request or simply ignore the invalid scopes. Your application should ensure all parameters are correctly formatted before initiating the authorization request. If the user's session with the authorization server times out during the authentication process, the server might return an error or simply ask the user to authenticate again. Authorization servers often have maximum session durations, which can expire if a user takes too long to complete authentication. Your application should handle timeout errors by allowing the user to restart the authentication flow. The token exchange phase has its own set of potential errors. The most critical PKCE-specific error is when the code verifier does not match the stored code challenge. The authorization server will return an error with code invalid grant and a description indicating that the code verifier is invalid. This could indicate an implementation bug where the wrong verifier is being sent, or potentially a security attack in progress. Your application should log this error for investigation, but should not expose detailed error messages to the user, as this could leak security-relevant information. Authorization codes have short expiration times, typically 1 to 10 minutes. If your application takes too long to exchange the code for tokens, the code will expire and the token endpoint will return an invalid_grant error. This can happen if there is network latency, if your application is suspended on mobile devices, or if the user's device goes to sleep during the process. Your application should detect expired code errors and prompt the user to authenticate again. Authorization codes are single-use only. If your application attempts to use the same code twice, perhaps due to a bug causing duplicate requests, the authorization server will reject that second attempt with an invalid_grant error. More seriously, many authorization servers implement authorization code replay detection and will revoke any tokens that were issued with that code, even from the first successful use. This is a security feature to detect potential code interception attacks. Your application must ensure it never reuses authorization codes. Network errors can occur at any point in the flow. The authorization request might fail to reach the server due to network connectivity issues. The redirect back to your application might fail to complete. The token exchange request might time out or return a network error. Your application should implement appropriate retry logic with exponential backoff for transient network errors, but should be careful not to retry authorization code exchanges, as codes can only be used once. State parameter mismatches indicate a potential CSRF attack or a bug in state management. When the authorization server redirects back, your application must verify that the state parameter matches the value it generated before initiating the flow. If these do not match, the response should be rejected entirely and treated as a security incident. The application should not proceed with the token exchange and should log the mismatch for investigation. PKCE with refresh tokens. Refresh tokens are a crucial component of OAuth 2.0 that allow applications to obtain new access tokens without requiring the user to authenticate again. When combined with PKCE, refresh tokens provide a secure way to maintain long-term access while protecting against various attack vectors. Let's explore how refresh tokens work with PKCE and the security considerations involved. A refresh token is a long-lived credential that the authorization server issues along with the access token during the initial token response. While access tokens typically have short lifetimes measured in hours, refresh tokens can be valid for days, weeks, or even longer. The refresh token allows the client application to obtain fresh access tokens after the current one expires, maintaining the user's authenticated session without interruption. To obtain a refresh token, the client must include the offline_access scope in the initial authorization request. This scope signals to the authorization server that the client needs long-term access. The authorization server will typically show this clearly on the consent screen, as granting offline access is a more significant permission than just immediate access. Not all authorization servers support refresh tokens for all client types, and policies vary about which clients are allowed to receive them. When the access token expires, the client uses the refresh token to request a new access token without user interaction. This is done by making a POST request to the token endpoint with grant type set to refresh token and including the refresh token itself. The authorization server validates the refresh token, checks that it hasn't been revoked, and issues a new access token. Some authorization servers also issue a new refresh token with each refresh, implementing what's called refresh token rotation. PKCE's role with refresh tokens is important to understand. PKCE protects the initial authorization code flow, ensuring that only the legitimate client can exchange the authorization code for tokens. However, once tokens are issued, including the refresh token, They become bearer tokens. Anyone who possesses a valid refresh token can use it to obtain access tokens. This is why refresh tokens must be stored extremely securely. Refresh token rotation is a security enhancement that many modern authorization servers implement. With rotation, each time the client uses a refresh token to get a new access token, the authorization server issues a new refresh token and invalidates the old one. This creates a moving target for attackers. If an attacker somehow obtains a refresh token and uses it, the legitimate client's next refresh attempt will fail because its refresh token has been invalidated. The authorization server can detect this as a potential security breach and revoke all tokens for that session. PKCE security vulnerabilities and mitigations. While PKCE significantly enhances the security of OAuth 2.0 flows, no security mechanism is perfect. Understanding potential vulnerabilities and their mitigations is crucial for implementing PKCE correctly and maintaining a secure authentication system. Let's examine various attack vectors and how to protect against them. One potential vulnerability is insufficient entropy in code verifier generation. If the code verifier is generated using weak random number generators or predictable patterns, an attacker might be able to guess or brute force it. For example, if an implementation used the current timestamp as the code verifier, an attacker who knows approximately when the authorization request was made could simply try timestamp values around that time. The mitigation is to always use cryptographically secure random number generators provided by the operating system or trusted libraries, and ensure the code verifier has at least 256 bits of entropy. Code verifier leakage is another serious concern. If the code verifier is stored insecurely, such as in plain text logs, browser local storage, or unencrypted files, an attacker who gains access to these storage locations can steal the verifier. Even storing it in memory is not completely safe on compromised systems where memory dumps or debugging tools might expose it. The mitigation involves using the most secure storage available for the platform, limiting the lifetime of stored verifiers, implementing proper access controls, and avoiding logging sensitive values. Downgrade attacks occur when an attacker forces the client to use weaker security mechanisms. If a client supports both PKCE with S256 method and the legacy plain method, an attacker might intercept the authorization request and modify the code challenge method parameter to plain. The client would then send the code verifier itself as the challenge, defeating PKCE's security. The mitigation is to only support the S256 method, reject any responses that indicate plain method was used, and ensure authorization servers reject plain method requests entirely. Authorization code injection is an attack in which an attacker tricks the client into using an authorization code the attacker previously obtained. The attacker authenticates to the authorization server as themselves, obtains an authorization code, and then somehow delivers this code to the victim's client application. If the client uses this code, it would receive tokens for the attacker's account instead of the victim's. While PKCE doesn't directly prevent this attack, proper state parameter validation does. The state parameter should be cryptographically random and verified to match, ensuring the response corresponds to a request the client actually initiated. Session fixation attacks involve the attacker setting up a session and then getting the victim to complete the authentication within that session. In the OAuth 2.0 context, this might involve the attacker generating an authorization request with their own state and code challenge, then tricking the victim into completing the authentication. The victim's successful authentication would complete the attacker's flow. This is prevented by proper state management and ensuring the state parameter is tied to the specific user session. PKCE and OAuth 2.0 specification evolution. Understanding the evolution of OAuth 2.0 specifications and how PKCE fits into this evolution provides important context for why PKCE is now considered a best practice. The OAuth 2.0 framework has undergone significant changes since its initial publication, with security considerations becoming increasingly important as real-world attacks have been discovered and analyzed. OAuth 2.0 was originally published as RFC 6749 in October 2012. This specification defined several grant types, including authorization code, implicit, resource owner password credentials, and client credentials. At the time, the authorization code flow was considered secure for confidential clients that could store client secrets, while the implicit flow was recommended for public clients like JavaScript applications that could not store secrets. The security model relied on TLS for transport security and client secrets for client authentication. However, as OAuth 2.0 was deployed at scale, particularly in mobile applications, security researchers identified vulnerabilities. The authorization code interception attack was demonstrated in practice against several mobile applications. Attackers showed that malicious apps could register themselves as handlers for custom URI schemes and intercept authorization codes intended for legitimate applications. Without client secrets, these intercepted codes could be directly exchanged for access tokens. PKCE was developed to address these mobile security concerns. It was published as RFC 7636 in September 2015, about 3 years after the original OAuth 2.0 specification. The RFC was titled Proof Key for Code Exchange by OAuth Public Clients and was explicitly designed for native applications. The specification introduced the code verifier and code challenge mechanism, providing a way to authenticate public clients without requiring them to store secrets. Initially, PKCE was considered an optional extension specifically for native applications. Many web applications and confidential clients did not implement it because they relied on client secrets for security. However, as the specification was deployed and analyzed, the security community recognized that PKCE provided benefits beyond just mobile scenarios. It offered defense in depth even for clients with secrets, and it worked well for single-page applications which were becoming increasingly common. In parallel, security issues with the implicit flow were becoming more apparent. The implicit flow returns access tokens directly in URL fragments, which can leak through browser history, referrer headers, and various other channels. Security researchers demonstrated practical attacks against implicit flow implementations. The OAuth working group began recommending against using implicit flow even for public clients. OAuth 2.0 Security Best Current Practice, published as a draft document and continually updated, began recommending PKCE for all OAuth 2.0 clients, not just native applications. This represented a significant shift in thinking. The document also recommended against using the implicit flow and the resource owner password credentials flow. These recommendations were based on years of real-world experience and security analysis. In December 2020, OAuth 2.1 was proposed as a consolidation and update of the OAuth 2.0 specifications. OAuth 2.1 is not yet finalized as an RFC, but it incorporates current best practices and lessons learned. One of the key changes in OAuth 2.1 is making PKCE mandatory for all OAuth clients, no longer optional. The specification entirely removes the implicit flow and the resource owner password credentials flow. These changes reflect the security community's current understanding of OAuth 2.0 security. OpenID Connect, which is built on top of OAuth 2.0, has also evolved its security recommendations. The OpenID Connect specification was published in 2014 and initially followed OAuth 2.0's approach of recommending implicit flow for certain client types. However, as understanding of PKCE improved, OpenID Connect implementers began recommending PKCE with authorization code flow for all clients. The Financial Grade API (FAPI) profile, which defines security requirements for high-risk applications like banking, mandates PKCE usage. The evolution of these specifications reflects a broader trend in security engineering, defense in depth, and eliminating unnecessary security variations. Rather than having different flows for different client types, the current best practice is to use authorization code flow with PKCE universally. This simplifies implementation, reduces the chance of configuration errors, and provides consistent security across all client types. For developers implementing OAuth 2.0 today, the key takeaway is clear. Always use PKCE regardless of client type. Use authorization code flow with PKCE for web applications, mobile applications, native desktop applications, and single-page applications. Do not use implicit flow or password credentials flow. If you are working with existing implementations that do not use PKCE, migrating to PKCE should be a priority. Most authorization servers now support PKCE, and many are beginning to require it. Looking forward, we can expect authorization servers to increasingly require PKCE and reject requests that don't include it. Some major identity providers have already announced plans to deprecate non-PKCE flows. The specifications will continue to evolve based on new security research and real-world experience. Staying current with OAuth 2.0 security best current practice and the OAuth 2.1 development is important for maintaining secure implementations. PKCE performance and scalability considerations. While security is the primary motivation for PKCE, it is also important to understand the performance and scalability implications of implementing PKCE in production systems. These considerations affect both client applications and authorization servers, and understanding them helps you design efficient, scalable authentication systems. From the client perspective, PKCE adds minimal computational overhead. Generating the code verifier requires obtaining random bytes from the system's random number generator. This is a very fast operation. 32 bytes of random data can be generated in microseconds on modern hardware. The base 64 URL encoding of these bytes is also extremely fast, involving simple bit manipulation and character mapping. The entire code verifier generation process typically takes less than a millisecond and is negligible compared to network latency and user interaction time. Computing the SHA-256 hash for the code challenge is also computationally inexpensive on modern processors. SHA-256 is designed to be fast to compute, and hashing a 43-character string takes microseconds. Modern CPUs often have hardware acceleration for SHA operations, making them even faster. On mobile devices, even older hardware can compute SHA-256 hashes quickly enough that the user perceives no delay. The total client-side computational overhead of PKCE is typically under 1 millisecond. Network overhead from PKCE is also minimal. The code challenge adds approximately 43 characters to the authorization request URL, and the code verifier adds 43 characters to the token exchange request. These small additions have negligible impact on network transfer times, even on slow mobile connections. PKCE testing and validation strategies. Thorough testing of PKCE implementation is critical for ensuring both security and functionality. A single bug in PKCE implementation could compromise the security of your entire authentication system. Let's explore comprehensive testing strategies for both client and server implementations of PKCE. Unit testing should cover all the cryptographic operations involved in PKCE test code verifier generation to ensure it produces values of the correct length and character set. Generate many verifiers and verify they are all unique, as collisions would indicate poor randomness. Test base 64 URL encoding to ensure it properly handles the differences from standard base 64, including using hyphens and underscores instead of plus and slash, and omitting padding. Test SHA-256 hash computation with known input-output pairs to verify correctness. Test the code challenge generation end-to-end. Create a known code verifier, compute its challenge, and verify the result matches the expected value. Test with various verifier lengths from 43 to 128 characters. Test with verifiers containing all allowed characters to ensure no character causes issues. Test that the same verifier always produces the same challenge deterministic behavior. Test that different verifiers produce different challenges, no collisions. For client implementations, test the authorization request construction. Verify that code challenge and code challenge method parameters are correctly added to the URL. Test that the challenge is properly URL encoded if necessary. Verify that all other required parameters are present. Test with different client configurations to ensure the authorization URL is correctly constructed in all cases. Test code verifier storage and retrieval. Store a verifier, then retrieve it and verify it matches the original. Test storage across application lifecycle events. On mobile apps, test that the verifier survives app backgrounding and foregrounding. Test that the verifier is properly cleared after use or after timeout. Test error handling when storage fails. Test PKCE interoperability and standards compliance. Ensuring interoperability between different PKCE implementations is crucial for the OAuth 2.0 ecosystem. Your client application might need to work with multiple authorization servers, and your authorization server might need to support clients from different vendors. Understanding standards compliance and interoperability considerations helps ensure smooth integration across the OAuth 2.0 ecosystem. The PKCE specification, RFC 7636, defines exact requirements that compliant implementations must follow. Understanding these requirements helps ensure your implementation will work with other standards compliant systems. The specification requires that code verifiers be between 43 and 128 characters long and use only unreserved URI characters. Authorization servers must reject verifiers outside this range or with invalid characters. Clients must generate verifiers meeting these requirements. The code challenge method parameter is critical for interoperability. The specification defines two methods, plain and S256. While the specification allows both, security best practices strongly recommend supporting only S256. However, for interoperability, your implementation should explicitly specify the method rather than relying on defaults. Always include code challenge method equal S256 in authorization requests. Future of PKCE and authentication security. As we conclude this exploration of PKCE, it is valuable to look at where authentication security is heading and how PKCE fits into the broader evolution of identity and access management. Understanding these trends helps you make informed decisions about authentication architecture and prepare for future developments. PKCE has become a cornerstone of OAuth 2.0 security, and its importance will only grow. The OAuth 2.1 specification, currently in development, makes PKCE mandatory for all client types. This represents a major shift from OAuth 2.0 where PKCE was optional. Once OAuth 2.1 is finalized and adopted, we can expect authorization servers to increasingly require PKCE and eventually deprecate non-PKCE flows entirely. Major identity providers have already announced plans to require PKCE for new applications. The elimination of implicit flow and password credentials flow in OAuth 2.1 simplifies the OAuth landscape while improving security. By consolidating on authorization code flow with PKCE for all client types, the specification reduces complexity and eliminates entire classes of vulnerabilities. This represents the security community's learned experience from a decade of OAuth 2.0 deployments. Future authentication protocols will likely continue this trend of simplification and focusing on proven secure patterns. Passwordless authentication is gaining significant traction and will likely become more common. Technologies like WebAuthn and FIDO2 allow users to authenticate using biometrics or hardware security keys instead of passwords. These technologies can be integrated with OAuth 2.0 and OpenID Connect flows, with PKCE still providing protection for the authorization code exchange. Device authorization flow, defined in RFC 8628, extends OAuth 2.0 to devices with limited input capabilities, like smart TVS and IoT devices. This flow also benefits from PKCE protection. As more devices connect to the internet and require authentication, secure device authorization becomes increasingly important. Future developments will likely see PKCE applied to new device types and use cases beyond traditional mobile and web applications. Privacy considerations are becoming more important in authentication protocols. Regulations like GDPR and CCPA impose requirements on how user data is handled. Future authentication protocols will need to balance security with privacy, minimizing the collection and sharing of user information. PKCE's design is privacy-friendly because it doesn't require sharing unnecessary information between parties. The code verifier is ephemeral and never leaves the client, minimizing the information available to third parties. Zero-trust security architectures are changing how organizations think about authentication and authorization. In zero-trust models, every request must be authenticated and authorized regardless of source. This increases the frequency of authentication and the importance of efficient, secure authentication flows. PKCE's minimal overhead makes it well-suited for zero-trust environments where authentication might happen frequently throughout a user's session. Post-quantum cryptography is an emerging concern for all cryptographic systems, including OAuth 2.0. Current public key cryptography could be broken by quantum computers, though practical quantum computers do not exist yet. PKCE uses SHA-256, which is believed to be resistant to quantum attacks. However, if quantum threats become real, PKCE might need to evolve to use post-quantum cryptographic primitives. Decentralized identity systems and self-sovereign identity are emerging paradigms that could change authentication architectures. These systems give users more control over their identity information and reduce reliance on centralized identity providers. Even in decentralized systems, the fundamental security problem that PKCE solves, protecting authorization codes from interception, remains relevant. PKCE principles could be adapted to work with decentralized identity protocols. API security is evolving beyond simple OAuth 2.0 access tokens. The OAuth 2.0 token binding specification and other initiatives work to bind tokens more tightly to clients and connections, preventing token theft and reuse. PKCE's concept of cryptographically binding authorization codes to clients serves as a model for these token binding efforts. Future token security mechanisms will likely build on PKCE's success. Continuous authentication and risk-based authentication are trends where the authentication system continuously assesses risk throughout a session and may require additional authentication if risk increases. PKCE fits well into these models by providing strong initial authentication. Combined with ongoing token management and refresh token rotation, PKCE helps maintain security even in dynamic risk environments. Developer experience and security are sometimes seen as conflicting goals, but the OAuth community is working to make secure authentication easier to implement correctly. Better libraries, SDKs, and frameworks are abstracting away complex details while maintaining security. PKCE implementation is becoming more automated in major frameworks and identity libraries, reducing the chance of implementation errors. Standardization and certification programs help ensure implementations are secure and interoperable. The OpenID Foundation certification program tests OpenID Connect implementations for standards compliance and security. In conclusion, PKCE represents a major advancement in OAuth 2.0 security that has been proven effective through real-world deployment. Its adoption as a mandatory component in OAuth 2.1 reflects its success. Thank you for your attendance. Please consider subscribing to the channel.